Hello. Let me just begin by saying, let's go Wildcats. This is going to be a video, well, I guess it already is a video, that is going to have all of me doing the 2012 stuff from your review here, including the free response question. And some words of advice. You definitely want to be familiar with this equation sheet. This is equations through chapter 9. I'm going to be referring to this, so you want to be as familiar as you can possibly be with what's on here and what's not on here. And the real AP test, assuming that it happens in its most natural form, is 45 minutes of free response questions. In the 45 minutes that you get, you're going to have to do 35 multiple choice questions. And let me just tell you, that is a sprint. So you don't want to get in the habit of dilly-dallying over these multiple choice questions. I try to pace out your tests in a similar way to what the AP test is going to be. So anyway, if you find that those are time challenging, that's something you can think about and try to work on. So let's go. We can use 10 instead of 9.8 if we want to simplify calculations. This, I think in 2012, they still were not letting us use our calculator for the multiple choice part, but you can now. Now calculator is allowed, and equation sheet, which used to be only allowed for the free response, now that's allowed all the time. So I'm going to follow those rules, because that's what you guys are going to see. All right, let's go. So let's see. A ball is struck at time t, follows this, so it's projectile. The following graphs show quantities possibly associated with the motion as a function of time. Assume that air resistance is negligible and that the positive directions are upward and to the right. Okay, so which of these graphs represents the horizontal component of the velocity? So for a projectile, if we're only paying attention to the horizontal velocity, gravity isn't changing that. That acceleration is only down. The horizontal velocity remains constant. So we're looking for a graph of something that's constant. So 1 would be E. And 2, which graph represents the vertical component? So the vertical component, it starts up at the very top here, it would be 0. This was just all horizontal, and then no vertical, and then at the bottom it's this, so it starts out positive, it's negative. The slope of this, if this was velocity time, the slope of that would be approximately negative 10 meters per second squared. So that's D. All right. Now, let's see. An object with an initial velocity v sub 0, as shown above, slides up and then down a long frictionless inclined plane. Which of the following is true of the object? So before I even look at that, this is just like, it's actually very similar to this, right? And if we're looking at its velocity, it's going to go up and it's going to go back down again. It's kind of like diluted gravity on this frictionless plane, where the acceleration, if we knew the angle of the ramp, the acceleration would be g sine theta. Right, so if the ramp's at 90 degrees, then it would just be 9.8. All right, so which of the following is true of the object as it moves? It has a constant acceleration when moving up the plane and a greater acceleration when moving down the plane. So you got to watch out. I mean, that's just ridiculous. I hope you didn't pick that. I don't mean that as a personal insult if you did, but seriously, that's absurd. It has a constant acceleration while moving up the plane and a smaller acceleration. I mean, it's got the same acceleration up and down. The acceleration doesn't magically change. Now, if there was friction, that is a different story, because friction always opposes motion. So if it was a frictionful ramp, then on the way up, friction would be like on the same team as the sine component of gravity, but on the way down, they would be on opposite teams. So you would, in fact, get two different accelerations if there was kinetic friction. But there isn't. It moves with a constant velocity. Oh, my goodness. It has the same acceleration as it moves up and down. Yeah. It has continually varying. So, okay. So hope you got that one. Number 5. If you look at I think there were, I don't know, maybe 21 out of the 35 questions from this set of 35 that are things that we can do now, knowing what we know now. There's still more physics to learn, of course. So that's why there's numbers missing. 3 objects are located on x-axis, center of mass. Okay, so to do center of mass, I do all of the locations. Remember, that's like x1, m1, plus x2, m2, plus x3, m3, divided by the total mass. Is that on the formula sheet? Yep. Oh, where is it? This could be an old version of the formula sheet. I think that... It is not on here. I think that on the new formula sheet they have something like this, that x center of mass is equal to the sum of all xi mi over the sum of all the masses. Something like that. I'll have to double check that. I'm sorry that I don't have that handy right now, but I'm pretty sure that they added that on there. So anyway, if it is on there, it's on there in a very symbolically dense form, so you just need to remember how to unpack that. And center of mass is a pretty easy thing, especially for us right now. We just did it, right? So anywho, x location is 0 times 3 plus x location is 3 times the mass is 5, and then 5 times 2 all over the total mass is 10. That's 15 plus 10 is like 2.5. Right? They used to, before it was calculator allowed, that all the numbers were real easy, but they pretty much stick to that. It's calculator allowed now in the multiple choice, but you hardly need it. Which of the following is equivalent to a unit of momentum? Well, momentum is kilograms times meters per second, right? Mass times velocity. So is a joule the same as that? No. Is a newton the same as that? No. A joule, just for review sake, a joule is, you could think of energy in a couple different ways. I think the thing that makes the most sense maybe is that joules are how we measure energy in work, and work is a force times a distance, or like the area under a force versus distance. So that area is going to have units of this times this, or newtons times meters, and a newton is a mass times an acceleration, kilogram meters per second squared. So that means this is kilogram meters squared per second squared. If you go down to the level of base units, a joule is that, a newton is this. Joules times seconds, that almost gets there. Newtons times seconds, yes, and that's in fact, that's how we think of impulse, right? Force times time. And that should be pretty fresh for us too. Newtons times meters, that's the same as joules. So that's D. 2 objects are dropped from rest from the same height. Object A falls through a distance this during time t. Object B falls through a distance this during time 2t. If air resistance is negligible, what is the relationship between these 2 distances? Okay, so what we want to have is distances. This is an exercise in what we would call proportional reasoning. So distance, if you think about, so this is constant acceleration. So what kinematics equations do we have? We have these ones. And this is the one that's really like distance as a function of time, right? Or position as a function of time. So if we're just interested in how far something has gone when it's dropped, we could say that its starting position is 0 and its initial velocity is 0. So position is a function of this. So the distance that something falls is 1/2. In this case, the acceleration would be g t squared. If you're wondering why I didn't make that negative, if these things are only going down, I can just choose down to be the negative direction. I'm just interested in the positive versions of these distances. So what happens if you double the time? So if you double the time, then you're going to quadruple the distance because the time is getting squared. So whatever you do to the time, that effect is going to get squared. If you triple the time, that's going to increase this by a factor of 9. So that means that dB is 4 times bigger than dA, because dA is the shorter time. So I guess they want it the other way around, so they would want like dA equals. So if I divide that over, that would be this. Right? Exercise in proportional reasoning. I think the easiest mistake would be to accidentally go that direction. This is not these answers are not recognizing that this gets squared. It's not a direct relationship. And boy, you sure have to be confident. If you're going to pick one of these answers, it cannot be determined from the information given. I would steer clear of that pretty much all the time. Every once in a while, but boy, you need to be so confident that that's the right answer. And there should be an answer choice F, because that might be what you have in your physics class. I cannot determine the answer from the given information, but that's not a choice. All right, so let's see if we can read this tiny print here. The maximum mass that can be hung vertically from a string without breaking the string is 10 kilograms. Okay, so that means maximum force. If you had 10 kilograms, that would be 100 newtons of gravitational force, multiplying by 10, right? I'm just taking their advice, 980, whatever. And then so the maximum tension in this thing is 100 newtons. That's what we're supposed to get from that. A length of this string that is 2 meters long is used to rotate a 5 kilogram object in a circle on a frictionless table with the string horizontal. Maximum speed the mass can attain under these conditions. So if this thing's moving in a circle on this table like this, with this 2-meter circle, then the only thing providing the unbalanced force toward the center of the circle is that tension. So I know that that force of tension must be equal to the mv squared over r that we need to move something in a circle. So if we want to max the speed out, we got to max that. It can't require more force than that. So the mass is half a kilo, v squared, and the r is 2. So multiply, that's like 1/4. So 400, the square root of 400 is 20. That's that. If the velocity was any bigger than that, then it would require more tension than this string can provide. Is this equation on the equation sheet? Yes, sort of. It's here, and this gives that centripetal acceleration. So you need to know, oh, well, force equals mass times acceleration, which is also in a slightly weird form. So just multiply both sides by mass, and that gives you the force equals mv squared over r. So being familiar with what's here and what isn't, super important. Number 9, an object moving on a horizontal frictionless surface makes a glancing collision with another object initially at rest on the surface. In this case, which of the following is true about momentum and kinetic energy? So this is an interesting thing that they're doing here. They're making us consider, what does this mean? We could observe this collision without having taken any measurements. And we wouldn't really know, like, the real question here is it elastic or is it inelastic? Like, is it a perfectly elastic collision? Glancing collision, so something bounces off something else, it could be elastic. It could be. It's definitely not, they didn't stick together, right? So let's see. Momentum is always conserved and kinetic energy may be conserved. I think that that is the correct answer because momentum is always conserved in a collision. Kinetic energy may be conserved. We don't know if this is elastic or not. It's a glancing collision. And to make that assumption that kinetic energy was conserved, we have to really be told it's an elastic collision. Kinetic energy is always conserved and momentum may be conserved. Because momentum is always conserved. Momentum is always conserved, yes, and kinetic energy is never conserved. No, it is because kinetic energy is conserved only if it's an elastic collision. Both momentum and kinetic energy are always conserved. Nope. Neither. Okay, so definitely this. All right. A particle of mass m starts from rest at position x equals 0 and time t0. It moves along the positive x-axis under the influence of a single force. So here's force as a function of time, where b is a constant. The velocity is given by, okay, so how do I get from force as a function of time to velocity? Well, I know my calculus relationships between these, where I can take derivatives to get that way, and then I can take antiderivatives to go that way, right? So, and of course, force is equal to mass times acceleration. Right, so if I replace that, then acceleration is equal to b over mt. And then to get back from acceleration to velocity, you need to take an antiderivative. So that would be, this b over m is just a constant, t squared, or 2, right? And plus c, but it starts from rest, so this would be 0. So that looks like this. Right, remember that little cartoon about I'm in this class and calculus is the easy part? This is that class. 3 blocks A, B, and C of masses 1, 2, and 3. A, B, C, easy as 1, 2, 3. Get it? That's hilarious. Respectively are initially at rest on a frictionless surface as indicated in the figure above. What force F has to be applied on block C to accelerate the 3 blocks at 2 meters per second squared? Well, you can go through and make a complicated force diagram and all that, but this force doesn't know that these are 3 separate blocks, right? As far as this force is concerned, it's pushing 6 kilograms. So force equals mass times acceleration, so the force needs to be 6 times 2, which is 12. That's it. Go ahead, you can make all the force diagrams, you can figure out like how much force there is in between here and so on and so on, but everything cancels out when you add all those together, and this force does not know the difference. An electrical motor provides 5, that's a half a watt of mechanical power. How much time will it take the motor to lift a tenth of a kilogram mass at a constant speed, 2 meters? All right, so let's see, what do we have about, this is a question about power, right? So they're giving us these 2 versions of that. Okay, and either one of these will work just fine for us. Also, this is, if you want the average power, I shouldn't put another equal sign there, average power is change in energy over change in time. So either one of these, I think, will work just fine for us. I'll show you how to do it both ways. So change in energy, if you're going to, let's see, if you're going to lift this tenth of a kilogram mass, and you're going to lift it 2 meters, then its change in gravitational potential energy is mg, I'm just going to use 10, h, so that's 2 joules. And in how much time, so if we're going to use power is equal to change in energy over change in time, then the power I know is half a watt, That's equal to change in energy is 2 over the time, so that looks like it's going to be 4 seconds. How about doing it the other way? What if I wanted to do the power equals force times velocity? Well, if it's going to be lifted at a constant speed, then the lifting force would have to be equal to the gravitational force. So the force of gravity on this thing is 1 Newton, right? It's mass times 10. So that force would have to be 1 Newton. So power is equal to force times velocity. So this is 1 Newton. Let's put a 1 there, leave the units out. And then the velocity is, if we're going to lift it at a constant velocity, that's distance over time, and that's 2 meters over time. And then the power is 0.5. So do algebra, you get 4. So either way, it is all the same. Here, a block slides from rest with negligible friction down the track above, descending a vertical height of 5 meters to the point P at the bottom, and then there's friction, and there's the friction coefficient. How far does the block slide on the horizontal surface before it comes to rest? Okay, so this is an energy problem, right? We got this here, mgh worth of gravitational potential. At the bottom, it's going to be kinetic energy, and then at the end, that work done by friction, force times distance, is going to knock that all out. So all of this energy here is eventually going to be tapped out by the work done by friction. So how much energy do we have here at the start? I've got, I don't know the mass, so I've got the mass of it times 10 times the height is equal to the work done by friction, and work is equal to, when it's a constant force, this is for constant force. Let's just check in with our equation sheet here. So there's your gravitational potential energy. That's there in this form, mg delta h. And what about work equals force times distance? That's given in this integral form only. That's always true. But from this, we should also recognize dr, why they're using an r, that's just kind of a generic vector thing. But this is just like our force with respect to position. This was f dx in your notes. And also for a constant force, work equals force times distance, times the cosine of the angle between them if there is one, right? So that's not here. So make note of that. So in this case, the force is constant. It's a friction force. What do we have for friction? Friction is less than or equal to mu times the normal force. If we're talking about kinetic friction, it is equal to, right? So this is kind of all the friction, or all of them, all 2 of the friction formulas put together. If it's static friction, then we're less than or equal to, right? Static friction, it's as much as you need to keep it from moving. If it's kinetic friction, then it is just equal, right? So mu times normal force. This is flat here, so the normal force is just equal to the gravitational force. So that force of friction is mu m g d. We've seen that expression come up lots of times. So mu m g, and then d is what we're looking for. So the m's cancel, the 10's cancel. This is the same as 1/5 multiplied by 5, so that's E. Oops, sorry. All right, number 14. Graph above shows velocity as a function of time. This is a velocity versus time graph. So the slope of this is acceleration, and the area under this is displacement. All right, velocity time, it's like looking at the graph of a derivative in calculus class. Lots of information in there. It shows velocity as a function of time for an object moving along a straight line. For which of the following sections of the graph is the acceleration constant but not 0? So the slope of this is the acceleration. So we want it to be constant but not 0. So that means it needs to be straight, right, and not horizontal. So that looks like RS, ST, RS and ST. The velocity of a particle moving along the x-axis is given as a function of time. Okay, so same things that we just said here about derivatives and antiderivatives. V is in meters per second, t is in seconds. What's the acceleration of the particle at time 2? Oh my goodness, I feel like I've got to go look at that cartoon again. Acceleration is equal to 6t minus 2, plug in 2, that's 10. Identical net forces act for the same length of time. Forces and times, that's impulse. So we should be thinking about impulse and momentum here. Forces and times, I'm thinking about impulse. Identical net force and identical time. So whatever is happening here, the impulse is the same, and the impulse is equal to change in momentum. Which of the following describes the change in the linear momentum? So they got to be the same. Right, because impulse equals change in momentum. So if it's same force, same amount of time, it's got to be the same change in momentum. A certain one-dimensional conservative force is given here. So that looks like if that reminds you kind of like force equals negative kx, like Hooke's law for this. That's spring force, but that is only for an ideal or linear spring. So this looks like some kind of similar thing here, but this we would call maybe like a non-linear spring. See those sometimes. F is in newtons, X is in meters. Possible potential energy function for this. Well, to get to the potential energy function, you take the antiderivative of this and you ditch the negative sign, right? That's how we do that. Is this on the equation sheet? Yep, right next to that. To remind you, look at that, to remind you of that relationship. So here I just need to do the same thing, take the antiderivative of that. So it looks like it would be 1/4 kx to the fourth and ditch the negative sign. And you know, you really don't want to like just crash through this. Like, oh, I've seen that before. That's probably it. No, that's not it, because this is not a linear spring. 25. A block of mass m is pulled across a rough surface, as shown above. The coefficient of friction is mu sub k. The force F that pulls the block is exerted at this angle phi. Which of the following is an expression for the magnitude of the frictional force on the block if it is moving at a constant speed? Constant speed. Forces are balanced. Let's make a force diagram. So got this force F broken into components here. This would be F cosine phi and F sine phi. Here's a gravitational force, which is mg. The friction force here is equal to mu sub k times the normal force. And the normal force is not equal to this, because this is helping out in the up direction. The normal force plus this would equal this. So just doing a slight bit of rearranging there. That means the normal force is this minus that. It's mg minus F sine phi. If you're wondering why I'm wearing a puffy coat while I'm making this video, it's because the windows in my classroom here are open to improve air circulation, and it's pretty cold in here. So mind your own business. So let's see. Force. Which of the following is an expression for the magnitude of the friction force? Okay, so what's equal to what here? I think that probably we need to combine this equation and this one, right? So the friction force is equal to mu, what do they call that? Mu sub k times the normal force, which is this, mg minus f times the sine of phi. And yep, there it is. All right, 26, two 4-kilogram blocks hang from a rope that passes over the two frictionless pulleys. What's the tension in the horizontal portion of the rope? Well, the tension in any part of the rope is the same, right? There can't be different amounts of tension if these are frictionless. If there's an intervening object, like if all of a sudden somebody grabs this with their, that's supposed to be a hand. Hands are really hard to draw. Everybody knows that. So this is a hand. If this is like the hand, the invisible hand of, no, it's not an invisible hand. I'm drawing it here. So if there is an intervening force here, then there can be different tensions on the two sides. But if there is not, then the tension in the rope, there's only one rope, so it's the same everywhere. And here, if this is 4 kilograms here, then that's 40 newtons of gravitational force. And these aren't moving, so there's 40 newtons of tension force balancing that, and that's it. It's real tempting. A wrong answer that I've seen many students choose for this is to go for the 80 newtons because, well, there's 40 here and there's 40 here, so there must be 80 there. And that's wrong because this rope doesn't know the difference between this. This is in equilibrium, but what if it was like this setup instead? What if the rope was just attached to a wall? I mean, either this thing's moving or it's not, right? So is it a wall holding it in place, or is it another 4-kilogram mass that's balanced against it on the other side? Don't know. There's no difference as far as this little rope is concerned here. All right. 27. Person throws a ball of mass 0.2 of a kilogram. Ball starts from rest, accelerates horizontally and uniformly through a distance of 0.9 and leaves the person's hand at 30 meters per second. Okay, so we've got a force applied through a distance. A force applied through a distance. So what does that make us think about? A force applied through a distance should make us think about work, which is equal to change in energy, in this case the change in kinetic energy. So this is what I need. Force times distance is equal to change in kinetic energy. And what was the kinetic energy? It started from rest, so it's just going to be this work turns into the kinetic energy. That's what we're looking at. So we're looking for the force, so that's going to be mv squared over 2d. So m v squared over 2d. They usually make these things pretty easy for like canceling stuff out. So the 2 and the 10, that makes a 1/5 and a 1/5, so those 1/5s cancel out, and then you get 30 squared over 9, so that's 30 squared is 3 times 3 times 10 times 10 over 9, so that's 100. You can do it with your calculator, of course, that's fine. Railroad car of mass 1,500 kilograms rolls to the right at 4 meters per second and collides with, we should be thinking immediately, collision, probably momentum, with another railroad car of mass 3,000 kilograms. It's rolling to the left. Right and left, watch out for the signs, cars stick together. The speed immediately after the collision is. So the momentum before is equal to the momentum after. So beforehand, we got 1,500 going to the right. I'll take that to be positive at 4 meters per second. And the other car of mass 3,000 going to the left at 3 meters per second. And afterwards, they're going to stick together, so the total mass is 4,500, and I don't know what their speed is afterwards. That's what we're looking for. So 6,000 minus 9,000 over 4,500, that's negative 2/3, right? Now what about the negative sign? Well, they're asking for the speed immediately after, so that's doesn't matter about direction. So looking for A. Number 31, ball 1 is dropped from rest at time t equals 0 from a tower of height h. And at the same instant, ball 2 is launched upward from the ground with initial speed v sub 0. If air resistance is negligible, at what time t will the two balls pass each other? I think this is a pretty tricky question. So here, let's make little position functions for both of these. So, and let's make them relative to the same place here. So let's call this y equals 0. So this ball right here, its position function, y as a function of time, would be equal to 1/2 gt squared, right? I'm using this. I'd like to do the terms in the other order because math habits, I guess, the square, and then so I'm just using this, right? Now this thing, it's dropped from rest, so its initial velocity is 0, and its initial height is h. So its position as a function of time is this. And if we take this to be the positive direction, then that acceleration would be negative, so the position would be decreasing as the time starts to tick by. That's the position of the first one. Position of the second one, it has the same acceleration, negative 1/2 gt squared. It has an initial velocity of v sub 0, but its starting height is it starts at 0. And we want to know when these two things are equal to each other, right? So if I set those equal to each other, those cancel out. And what time t? So looks like I just have to divide by that. Right? That's all. I think I must have done this last time I did that problem. I must have done it a different way because that seemed a lot easier than whatever I did last time. So do it this way. That's good. And last multiple choice, a ball of mass m falls vertically, hits the floor with a speed v sub I, and rebounds with a speed v sub f. What's the magnitude of the impulse exerted on the ball by the floor? I don't know if we really looked at the impulse and momentum stuff here. So there it is. Impulse equals change in momentum, and that's the integral of force with respect to time. And of course, momentum is mass times velocity. So impulse is equal to change in momentum is the key right here. Impulse is equal to change in momentum, and that's what they want to know, the magnitude of the impulse. So magnitude means positive version. So let's see. The change in momentum is mass times final velocity times mass times initial velocity. It hits the floor with a speed v. Now, we need to be careful here because we can't, they're saying magnitude, but I can't treat both of these as speeds. Like, I have to respect the direction here. And then my final answer I can make positive. So I'm going to say that down is negative, and that up is positive. So that means mass times the final velocity, it rebounds, this is up. So that's positive. minus mass times, now it's going down, its initial velocity is down at that speed. So the magnitude of the impulse is m times vf plus vi. And you have to be, I think lots and lots of students would pick this. That's a real easy mistake to make with impulse and momentum, to not handle the signs of those, especially since they said these are just speeds. We had to make sure that we got that change correct. Okay, so what about free response questions? This is kind of a slightly unusual free response question, but they do like to incorporate little elements of experimental design into free response questions. This one's unusual because it is just a full-blown, the whole thing, all 15 points of it are experimental design. So how do you approach free response questions in general? You should think of them as 15-minute questions. That's how much time you'll have. You'll have 3 of them on the real AP test. 3 times 15 minutes is 45 minutes. You are to perform an experiment investigating the conservation of mechanical energy, a transformation from gravitational potential energy to translational kinetic energy. This, if you're wondering, whoa, what does that mean? I've never heard it called that. It's because pretty soon in a couple of chapters, actually just in one chapter, I guess, we're going to also talk about rotational kinetic energy. So that's why they said that. This just means regular old kinetic energy, 1/2 mv squared. So talking about mgh turning into 1/2 mv squared. Okay, so in an experimental design, and a lot of the problems, a lot of the little experimenty kind of problems that they have when you have to like make a little graph, whatever, the thing that they're doing in that experiment is probably going to be pretty similar to one of the things that I had you do a lab with for. So you should think of, like, don't try to invent some crazy thing. Try to think of something here that is familiar. So gravitational potential energy to translational kinetic energy. You could drop something. You could do some kind of cart on track thing. And there's different things that you could do, but you definitely need something to be changing height, right? So let's see, instead of going through and like making up some answer myself, I'm going to take you through the scoring guide. I think it's a good idea also for you to get familiar with what these scoring guidelines look like. These are really easy to find. These are not like protected or anything. You can just look these up on the internet. If you just type in AP Physics C Mechanics 2012 scoring guidelines, it'll have the scoring guidelines for all 3 questions in one document. So 15 points total is how they score these, as opposed to like the 9 points that calculus FRQs are worth. So let's see what they said. The first point, for choosing the meter stick and the stopwatch regardless of what else is checked. So they thought that that was important. That's only 1 point important, but you got to have the meter stick and you got to have the stopwatch. So 4 points here for a procedure that indicates the height needed to calculate the gravitational potential energy, for a procedure that indicates the distance and time measurements to calculate velocity. So since we're doing like a UG to 1/2 mv squared, this is an mgh to a 1/2 mv squared, you're going to need to know what the h is and you're going to need to know what the v is, right? So how are you going to find that h? Well, you're going to talk about that in your procedure. How are you going to find this v? Got to talk about that in the procedure. A procedure, you should think of the guiding, if there's one guiding principle for what you need to say in the procedure, and also what you don't need to say, you need to explain how you're going to use the equipment to get the numbers. That's what the procedure needs to do. So tell me, like, if it's a recipe that I can reproduce, then tell me what things I need and how I should use them to be able to get the right numbers. For a diagram and clear indication of the height measurement, and then a diagram for the distance measurement. So then after that, they have some examples, like here's that half-Atwoods machine. And you can look this out, or you can pause and read through those things. That's one way of doing it. And here's another, cart down a ramp. We did that. We didn't do that in terms of, did we do that with energy? We did the little ice puck going up the ramp. Of course, dry ice puck was not one of the choices there. So similar to that. And then in part C, those are not the only two things that you could do, of course. For a clear indication of the initial potential energy, for a clear indication of the final. So I thought this was interesting that they really wanted like the UG initial plus K initial, even if this was 0. Now, I was never really quite sure when I've assigned this problem in the past how to deal with this. Like if you didn't include this, if you just had UG initial going into K final, like if these were 0 for you. I think a lot of the different experimental designs would have those be 0. So, not sure. And then correct calculation of the instantaneous velocity of the system. So that's where you're going to take your, like actually do this and get that. So here's the example that went with how they did it with the half-Atwoods machine. And here's how they did it with the cart on the ramp. And then the last points, 2 points here for answering D and E, which is what? The increase in energy and the decrease. So I'll let you look at those. Friction is always going to tap energy out. But an unintentional increase, then there must have been some extra energy put in the system somehow. There you go. That's a scoring guide for a free response question. That's a long video. Hope you enjoyed and hope that was helpful for those 2012 review problems.